Hi guys, I am Suryanarayan Mohanty from Geeta Bhubaneswar. So, today we will be discussing how to solve the problems on AC. Okay. So, when you will be facing the problems on AC, so you will be dealing with different type of circuits such as resistive circuits, RL type circuits, inductive circuits, purely capacitive circuit, purely inductive circuit, RL circuits, RC, then RLC. So, we will be dealing each one. So, how to solve the problems on this AC? Generally in these problems, what are the things those are being asked? One is the current, you have to find what is the current in a particular circuit, power factor of the circuit, impedance, power, etc. So, let us see first for a resistive circuit, how we will be dealing with a purely resistive circuit. So, we know that in AC generally we are dealing with the impedance. So, when we are dealing with a purely resistive circuit, at that moment the impedance is nothing but Z is equal to R, and if the voltage is given, current we can easily find I is equal to V by Z or V divided by R. And we know that the power factor cos phi is equal to R divided by mod Z. So, it is R divided by R. So, that is equal to 1 for a purely resistive circuit, and we know that in a purely resistive circuit both the voltage and current will be like this, and the phase angle between them is equal to 0. That is why this cos 0 is equal to 1. So, when we will be facing a problem on the purely resistive circuit, so directly we can put the formula. Next, when we will be going for a inductive circuit, this is a resistive circuit. When we will be going for a purely resistive circuit, purely inductive circuit. So, in a purely inductive circuit, your Z is equal to the magnitude of the Z is equal to XL, which is nothing but omega into L, or which is nothing but 2 pi f into L, and the unit of this impedance, as you know, it is always in ohm, and this XL is called your inductive reactance, and this is called your inductive reactance. And in a purely inductive circuit, the current lags behind the voltage by 90 degree. That is why when we will be finding the power factor, it is equal to 0, because you know cos of 90 degree is equal to 0. And when you are going to represent it in a complex domain, this is represented, L is represented by J X L. So, this is the case when we are dealing with a purely inductive circuit. Next, when we will be dealing with a capacitive circuit, purely capacitive circuit. In a purely capacitive circuit, the impedance is generally represented by Z is equal to minus J X C, where X C magnitude is 1 divided by omega C, its unit is also ohm, it is called your capacitive reactance, and here in a capacitive circuit the current leads by an angle 90 degree. So, here also your cos phi, your power factor is equal to 0, cos 90 is equal to 0. Now, we will see when we are going for combination of these elements, that is, now we will be dealing with RL, RC and RLC type circuit. Generally, the problems on the single phase AC, they are mainly asking the question from these three portions, either it is a RL, mainly the questions are on RL, RC or RLC. So, when first let us go for the RL circuit. So, when you are dealing with a RL circuit, so first of thing you have to find the impedance of this particular circuit. So, the impedance is nothing but you know that the L, if you want to represent it in ohm, it will be represented by J XL, which is your inductive reactance. So, in a RL circuit your Z is equal to R plus J XL, where XL is your inductive reactance whose magnitude is omega L or 2 pi FL ohm. Where you are going to find a magnitude of this, it is equal to R square plus XL square root over. When you are going to find the angle, you know from complex algebra tan inverse B by A, you can use your calculator or manually also you can find the angle, and you can represent this in the format mod Z angle theta or mod Z angle phi. Next, here the formula for finding current is remain same for all the thing. Your I is equal to magnitude of current is equal to V by mod Z, and cos phi power factor is equal to R by mod Z. So, when we are dealing with a RL type circuit, you just remember the angle between the voltage and current will be somehow like this, and it lies between 0 to 90 degree, not 0, not 90, because you know in a purely resistive circuit the angle between voltage and current phasor is equal to 0, and a purely inductive circuit it is 90 degree. Though we are taking a mixed circuit, a RL circuit, so it will never be 0 or 90, but it will lie in between that. This is the thing that you have to remember if you are facing some MCQs in some entrance examinations, and if you are getting the values somehow in between 0 to 90 and the other values, other 3 values are beyond that. So, you can easily tick the answer which lies in between 0 and 90. So, here there is a common question. So, when we will be solving the questions on this RL circuits, suppose I am taking a simple example. Suppose this is equal to 6 ohm and here it is given 8 ohm, and it is asked to find the total impedance of the following circuit. So, here what you can write, you can easily write it is 6 plus j 8 ohm. Why? Because look, here it is the value of the reactance, not the value of the inductance, because if the value of inductance will be given, it will be given in Henry, but here it is given in ohm, that implies this is your XL value. That is why you can directly write Z is equal to R plus J XL, the formula that you are using to find the impedance of a RL circuit. But somehow if it is given like this, it is 6 ohm and it is given 8 Henry, frequency is given suppose 50 hertz in a particular question. So, there you can't write it is 6 plus j 8, because its unit is ohm, whereas its unit is Henry. So, you have to convert this into ohm. So, here you have to find the XL, which is nothing but omega L, or it is 2 pi f into L. So, it is 2 into 3.141 into 50 into 8. So, what are the value you have to find, and it is in ohm. Then you can directly write Z is equal to, it is R plus J X L. So, this is the thing that you have to mark, whether the unit is given in Henry or it is in ohm. If it is ohm, no need to worry, directly you can write, but if it is in Henry, you have to convert it into ohm, then you have to find the total impedance. And once you find the total impedance, you can find the other values, current, power factor, the other things we can easily find by putting our general formula, that is I equal to V by mod Z, and your cos phi is equal to R by mod Z. Next, your RC circuits. So, when you are dealing with your RC circuits, so here your Z is equal to R minus J X C, because C is represented as minus J X C in complex form. So, when you are going to find its magnitude, it is equal to Z is equal to R square plus X square root over. Directly by using your scientific calculator, you can convert it into polar form, and manually also you can put the formula tan inverse V by A for that. Here also the same thing, voltage, if voltage is given, current magnitude is equal to V by mod Z, and your cos phi or power factor is equal to R by mod Z. So, here also the same thing as of your RL circuit, if both the units are ohm, if this is 6 ohm and it is given 8 ohm. So, you can write Z is equal to 6 minus J 8, but if it is given in farad, just like this R C, suppose this is R is given 100 ohm, C is given suppose 100 microfarad. So, you need to convert this farad into ohm by putting the formula minus J X C, where X C is equal to 1 divided by omega C. Next, we will be moving to your RLC circuits. Next is your RLC. It is a simple RLC network. Current is I suppose. So, here your impedance Z, this is a RLC series circuit, R, L and C are connected in series. So, your Z is equal to addition of each individual reactances. So, Z is equal to R. For inductance, you can go for JXL. For capacitance, it is minus JXC. So, this is your impedance of a RLC series circuit, and the magnitude of this you can easily find. This is R plus J XL minus XC mod Z R square plus XL minus XC whole square root over, and you can find the power factor cos phi, same formula, R divided by mod Z. Here there are 3 cases in a RLC series circuit. There are 3 cases. There is case 1, if XL is greater than XC. Second, if XL is less than XC. Third case, if XL is equal to XC. There are 3 cases for this RLC series circuit. When your XL is greater than XC, look here, if XL is greater than XC, then you will be getting a positive quantity over here. Somehow you will be getting Z is equal to R plus J something, suppose R plus Jx or some value. So, at this moment the circuit behaves like a inductive circuit, not purely inductive, inductive circuit. The circuit will behave as a inductive circuit. When you will be getting, when your XL is less than XC, you will be getting a negative quantity, your Z is equal to R minus J something. So, at this particular stage it is behaving as a capacitive circuit, and when you are taking your XL is equal to XC, at this particular stage your Z is equal to R, and this condition is called the condition for resonance. This is the resonating condition or resonance, we are simply saying this as resonance, where your XL is equal to XC. So, from this we are finding the resonating frequency for a RLC series network, that is when your XL is equal to XC. Suppose let us take the omega as omega 0, omega XL is equal to omega L, as you know, XC is equal to 1 divided by omega 0 C. So, omega 0 square is equal to 1 by L C, or omega naught is equal to 1 by L C root over. So, this is the expression for your resonating frequency. From this we can find F 0 resonating frequency, that is equal to 1 divided by 2 pi root over of L C. So, if in a particular question it is given that the circuit is under resonance and you have to find the resonating frequency, then you can directly put this formula and you can find the resonating frequency, and at resonance your XL is equal to XC and your Z is equal to R. So, if we summarize So, if we simply summarize the different type of circuits, AC circuits, simply RLC, RL, RC, RLC, and if you are writing the value of Z over here, here Z is equal to R, here Z is equal to JXL, here it is minus JXC, here it is R plus JXL, here it is R minus JXC, and here it is R plus J XL minus XC. For all the type of networks, your cos phi value, the formula remains same, R by mod Z. Magnitude of the current I is equal to V by mod Z. So, another type of problems are coming from the single phase AC regarding the complex power. So, this is the summary for the impedance, power factor and current. How to find the current, power factor and impedance of this type of circuits. Next is your complex power. Suppose in a particular question both voltage and current are in complex. In that case we can find the complex power S. Here V is in complex, let it is Vc, I is also complex, that is Ic. So, your S is equal to Vc Ic conjugate, the sign for conjugate. So, finally, you will be getting P plus minus j q, you will be getting a real term, you will be getting an imaginary term, because both the terms are complex. So, if when you multiply, then you will be getting a real term and there is an imaginary term. So, this is your real power and this is your reactive power. Suppose a simple example I am taking, suppose your B is equal to 2 plus 3 I or 3 j. So, in some books it is given I, in some books it is given j. So, I am taking 2 plus 3 I or I 3, I is given suppose what you can take 5 plus I suppose. So, here if it is given, find the complex power, find the real power, find the reactive power. So, simply what you have to do, your S is equal to V I conjugate, and conjugate you know already from complex algebra, V is 2 plus 3 I conjugate is nothing but 5 minus I. You can easily multiply these two things by using your scientific calculator. Manually also you can multiply 2 5s are 10 minus 2 I plus 3 I into 5, that is plus 15 I minus 3 I square minus 3 I square. So, it is 10. So, this is plus 13 I minus 3 I square is plus 3. So, it is 13 plus 13 I. Is it correct? Yes, 2 5s are 10. Let me verify, minus 2 I plus 15 I minus 3 I square. So, I square is, you know, I square is equal to minus 1. So, it is plus 3, 15 minus 2, that is 13, 10 plus 3, yeah, is it. So, from this you can find this is the real power P and this is the reactive power, and you know the unit of real power is watt, kilowatt or megawatt, and the reactive power unit is volt ampere reactive or kVAR, kilovolt ampere reactive or mega volt ampere reactive, and apparent power unit is volt, sorry, and apparent power unit is kV we are taking. If you are taking V is in volt and I is in ampere. So, the unit of apparent power is your volt ampere or kilovolt ampere or mega volt ampere. So, the last formula of this single phase AC perhaps is on if the voltage, current and power factor is given, how to find the power. That is, if V is given, I is given, not necessarily complex, and if cos phi is given, how to find the power. So, the active power P is equal to V I cos phi, the reactive power Q is equal to V I sin phi, and the apparent power is equal to V I, simply V I. So, these are the summary of your single phase AC. So, in next class we will be dealing with your 3 phase circuits. Thank you.